Hi, everybody. Dermot O'Shea here, host of the Antenna Podcast. I'd like to welcome you to another Antenna Podcast. Today, I'm delighted to have my friend Argy Petros. Argy, would you like to introduce yourself?
Yes. Hi, everybody. This is Argy Petros. Thank you, Dermot, for including me in your podcast. I can tell you about my career.
Yeah,
Uh,
give us a quick intro to Argy and where
okay.
you're
Yes.
based and what. Yeah.
I received my education from Virginia Tech. I got my bachelor's, master's, and PhD all from Virginia Tech in the 90s. And after that, I worked for Motorola and then XM satellite radio and then Think Wireless and now Taoglas.
Okay. And did your bachelor's was that in electrical engineering, I presume?
Yes, yes,
Okay.
everything in electrical engineering, and I got interested in antennas actually during my PhD.
Okay. So what
So
what what drew your interest to antennas?
okay, so halfway during my PhD, I was involved in my research, and that was really very theoretical, dealing with a lot of equations, electromagnetics, physics, mathematics, and I'm like, you know what, I need to do something more practical. So I started. I guess I had an interest on antennas, and I was lucky at that time. Virginia Tech had two of the best professors in the field. One was the antenna Stutzman, the Warren Stutzman. He's a professor from Virginia Tech. He's retired now, and I'm sure a lot of antenna engineers know his name. And that's when I got involved in the antenna lab. I took the class and I designed my first antenna, which was the Archimedean spiral antenna. Uh, at the same time, at Virginia Tech, we also had the Professor Theodore Rappaport, and he was a pioneer actually in wave propagation, cellular communications, and I was also very lucky to be involved there in that class, and I gained a lot of knowledge, practical knowledge, and
Mm.
that's when I got my tools to face the world. And in so before I finished my PhD, I had an opportunity of going to Motorola as an intern, and that was in Plantation, Florida. That's when the design antenna design work started. That was designing real antennas.
Okay. And you said like when you were doing your PhD, this had the practical element because we see a lot of customers who say, I've done antenna theory in college. I've read about this online, or I can use MATLAB to do my antenna.
Yes.
Right. So there's a lot of describe to me how important it is to know the practical piece and not just the theoretical piece.
Yeah, I mean, people. I see a lot of students at university. They always learn about antenna theory. I mean, that's all in the books. But you really, I think what the universities are missing is it's a practical antenna class that prepares you for the industry. So a lot of students they learn about, let's say, basic antennas like dipoles, monopoles, but really they haven't seen. Most of them have not seen any real antenna unless they go out to industry.
Okay.
So
So what was your first? You said you got in. The Motorola was the first real antenna. Like what was the real
yeah,
antenna?
so that group actually was called the CT2 group. That was the cordless telephone system, and that was in the 90s. It was a system. Actually, it was something between cordless telephones and cellular telephones. At that time, in the early 90s, cellular phones were very, very expensive, so people couldn't really afford them. So Motorola came up with a system where you have a cordless telephone at home and you're able to take it outside with you.
Yeah.
So that was the transition time between yeah, just before cellular telephones.
Yeah, I remember that. Yeah.
And I was designing there. I designed the base station antennas, which was a small base station, and and also the handset antennas, which are basically retractable helices, like the original cell phones.
Yeah, the telescopic
Yes,
antenna.
the telescopic antennas.
And they were just like singular dual band, right? They would have been
Yes,
like PCS or
actually,
something.
that antenna was just a single band, was the 800 megahertz band, and it was interesting because it was a low power system, so you had to have a base station every like 300 feet.
Okay.
So that system actually started to become popular in Hong Kong and Bangkok, Thailand, where they built thousands of those base stations. So people in the city were able to take their cordless phones from home and take it outside and communicate.
And but that's something I see a lot of today, right? If you look at a cellular antenna, we had dual band, whereas now
Yes.
we have to cover like 600 megahertz to 6 gigahertz with one cellular antenna, and the device might probably needs two or four cellular antennas. Like, how have you been able to transition from, you know, what you thought was a challenging antenna in the 90s to something we need today, which is you need it smaller, you need it like to be able to make it in high volumes, you need it cheaper, and you need a better performance, but you have like all these extra frequencies in there. How have you been able to like overcome that challenge?
Well, right, yeah, right now antenna work is very challenging, and when you're dealing, let's say when you're dealing with actual products, the antenna engineer actually is limited to a small space, and that antenna, as you said, needs to cover a lot of different frequencies, and uh, and this is really a challenge. So I guess simulation tools are important for that, and a lot of it really is hard work. A lot of antenna work is hard work. You
Okay.
can start with simulations, but you have to sit down on the bench and spend hours and hours of designing your antennas and testing them, and keep optimizing until you have something ready. So it is a lot of work, and a lot of it is, I can say, is black magic too. So
Well, what do you mean by that, right? So are you saying it's okay? So one, I like that. It's you need hard work and persistence to keep doing the retesting and the re-optimization. But when you say the black magic, like how do you come up with the black magic? What's your maybe it's is it an inherent thing that you just have that's mathematics related, or is it something you have to work on and train, or is it
I think you have to work on it, and it takes, I would say, it takes years. It takes years after designing hundreds of antennas. Then you can become more efficient in designing the antenna. So instead of taking you, let's say, a couple months to design an antenna, now you can spend a week and design an antenna based on your experience.
and is it
So a lot of
intuition then? Is it an
yes,
intuition? Yes.
a lot of it is intuition, and but obviously the simulation tools are very powerful now, and it's very easy really to create the geometry you need to simulate these antennas. In the old days, let's say the 90s and early 2000s, the most challenging part of antenna simulation was generating the geometry around the antenna.
Okay.
So
You mean the structure of the antenna itself, or the physical
yes,
world the antenna is going to live in?
yes. So because the antenna by itself is easy to design, right? So you design a monopole, a patch, anything. But a standalone antenna is very easy to design.
Hmm.
But now take this antenna and put it inside a phone with limited space or inside a device and with a lot of metal around, a lot of so so everything changes. So you can really, in order to simulate that, you have to really import all this geometry there in the tool. And I think
Okay.
now we are really we have the capability of doing that. But still, after simulation, you still have issues with designing the right antenna for your device, because the simulation tool really does not include other factors, like, let's say, digital signals that interfere, that picked up by the antenna, and now your sensitivity is not the same. So there's a lot of clock frequencies there, and this can interfere with the antenna. So
Okay.
now you have to go around it and move the antenna parts away from those circuits, or reorient PCB traces in order to have a system that works, an antenna that works in your system, not just a passive antenna. You can have, for example, the device and the passive antenna. You test it, everything is great, the antenna is good. But when you turn everything on, all of a sudden, your device is not delivering the performance.
Yeah. And how would you test? Like, what do you test? How do you test the antenna to see what the effects of the
Well,
device?
in the real world, you tested using, let's say, you test the sensitivity, you test the antenna, the range of the device, depending on if it's a phone, depending on the device, you have different tests. So again, you have to really meet those specs. Once you meet the specs, then you design the right antenna. And that means the antenna with everything working, not just a passive antenna.
Yeah. But like, what test are you performing on the antenna to make sure that you're going in the right direction?
Well, the antenna itself, I would say, again, it depends on the device and the system you're working on. And let's say for antennas inside devices, like mobile devices, efficiency will be the parameter you look at.
Okay. So maybe explain efficiency to us and what that is and how
Basically, efficiency is how efficient the antenna is. You give the power to the antenna, and the antenna delivers the power. Let's say power in, power out. So if the antenna is not optimized or matched correctly, then the efficiency will be poor, which means the antenna receives, the antenna, there's power available to the antenna, but the antenna does not take advantage of that power. So
it's wasting the power.
it's wasting the power, it's wasting in the mismatch because of mismatch loss and other parts of the antenna design. So, but now efficiency is the parameter, in this case, is a good parameter to use for antenna performance. However, when you're dealing with antennas, let's say mobile antennas on vehicles, you can't just use efficiency as your antenna performance parameter, because efficiency measures efficiency all over a 3D structure, 3D sphere. So let's say a car antenna receives the signals at low elevation angles. So let's say between 0 and 15 degrees elevation angles. So let's say you have a great antenna efficiency for that antenna, for the car antenna. However, sometimes most of this antenna gain is pointing up. Let's say for elevation angles 40 degree to 90 degree. So even though the efficiency looks good, the antenna may not be performing well because the gain at low angles is not good enough. So in mobile antennas for trucks and vehicles, we care about the most important factor is the antenna gain over low elevation angles.
Okay. Because we get customers a lot that say that I want the antenna with the highest gain. So it depends on their use case, is what you're saying.
Depends on the use case. Yes, exactly, on the application. So let's say I design a 5G antenna. In the low frequency case, let's say 600 megahertz, 700 megahertz. And my antenna is very small now because of cosmetic issues, aesthetic issues. I want to make it very short, very small, low profile antenna. And let's say I measure the efficiency, and the efficiency is great. It can be 60, 70%. But those low height antennas, most of the gain is pointing up. to the sky. But most useful signals are coming from low elevation angles from towers, right? So I can't really use efficiency as a measure of antenna performance. What I care about is the antenna gain in this case, right? In this case, we care about antenna gain at low elevation angles.
Okay.
So now when you're dealing with the cell phone or the smartphone, for example, then you do care about efficiency. You say, yes, efficiency, I agree with that right now. Efficiency is the only measure because now you hold the phone all kinds of directions, right? So you care about the efficiency. So again,
Gotcha.
efficiency is not it's not necessarily the only measure for antenna performance.
It depends on, yeah.
And,
It depends. You have to
and
think about the use case and the direction of operation, etc. And yeah.
yes,
And
so
and how would you test for efficiency? How do you test it?
well, efficiency obviously you can test it in an antenna chamber, or in case of let's say in case of a smartphone, you use a special chambers. We call them reverberation chambers, right? So what they do, they have metal structure there, moving metal structures. They can be fans, can be anything that basically simulate a signal that is, let's say, simulates the real world, basically arriving from all kinds of directions,
Okay.
and then you measure the antenna gain from that, from all those directions, and you come up with an efficiency number. But
Gotcha.
for a car antenna, for antenna mounted on a vehicle roof, you can test it in the chamber with different elevation angles. So basically and then eventually after that, you test it in an antenna range. You test the antenna in the antenna range on a vehicle with different elevation angles.
Okay. So you're trying to, that's where the average comes in. You're testing it at all the different angles, hence giving
Yes,
you,
and obviously you need the right tools, right, for
yeah,
measure your antennas
of course, yeah, yeah.
for the different applications. And then of course eventually you test the antenna with a fully working system. The antenna is not just, the antenna is part of a device. That's how we have to think about it, testing the antenna, part of the device. So the ultimate testing is when your whole system is working. Your whole system meets the specifications. That means you designed the right antenna.
Okay. Makes sense. Yeah. Interesting. So you said XM was your next port of call. I presume there was some sort
Yes,
of a Greek connection there.
yes. Actually, my manager he came from Greece, just like me. His name is Taoglas, and he's a brilliant engineer. He's the one actually, probably I would say, responsible for developing satellite radio uh, on time, and and that was actually a pretty challenging project. This is
Mm,
a perfect example of designing an antenna in the lab and it looks good, and you take it outside and things are not working.
okay.
So, so
Why is that?
basically,
Because of all the atmospheric noise or something, or
no, just okay. So satellite radio. Remember, satellite radio is not just satellite radio. I know maybe a lot of people don't know it. It's you have a terrestrial towers and the satellite radio signals. Signals are coming from towers, land-based towers, and and satellites. So the reason for that is when let's say you're driving around a city with tall buildings, your satellite signals will be blocked because of the buildings.
yeah,
So that's why satellite radio incorporates these land-based towers, especially in the big cities, to make up for that loss of service.
okay,
So in the lab, we're designing satellite radio antennas in the beginning. So we put them on the roof. We have a big box for a receiver and drive around. And in some locations, we could not get any signals. We lost the signal completely. I'm like, what's going on here? So basically, it was all the interference from all the other towers. Can be cell phone towers, will be UHF towers. we're getting all kinds of interference there. So again, this is the perfect example of the antenna in the lab looking great, everything is great, and then you go to the real world, field testing, the antenna fails. So it turns out it was all this interference from all the other systems. So we have to go back and design the low noise amplifier to incorporate filters and also improve the compression point of the amplifier so it doesn't compress as you have strong signals interfering with that. So you have a very weak satellite radio signal coming from 22,000 miles away, and you have all these towers, terrestrial towers, that transmit at high powers. So it was really a challenging. That was I would say one of the most challenging projects, designing the correct the antenna, basically the inline amplifier and the passive antenna for satellite radio.
Okay, interesting though, yeah. And then it really took off.
Yes.
So you went on then to set up your own antenna company. What
Yeah.
inspired you to do that?
Well, after working for companies, I decided to work for myself, and I'm like, why not? Let's try it. Let's try create like everybody wants to have his own company, right? His or her own company. So I left satellite radio and I started my own company. Initially, I was doing consulting, helping companies design antennas, several types of antennas and amplifiers. And at some point, I'm like, why only consulting? Why can I design my own products and sell them too? So I designed my first commercial product, which was a satellite radio truck antenna that mounts on a mirror on the heavy duty trucks. So, and obviously that the experience in satellite radio helped me, and I was probably one of the best people to do that. So I got lucky there, and that was my first commercial product. And that was a truck antenna. It was basically a quadrifilar antenna with an amplifier underneath. So basically a circular polarization, right? The satellite radio is all satellite signals, pretty much most satellite signals are circularly polarized. So the antenna.
How are you getting over the challenge of the terrestrial towers then if you have this circularly polarized antenna for the satellites?
No, well, the antenna will receive any kind of signals,
Okay.
right? So you have to make sure you filter all the other signals out.
Yeah. So at this stage, you knew you had the know-how to do XM
Yes.
satellite radio.
Yes, because I used my past experience, and that was my first product, the satellite radio.
I remember some antennas in the cars in the shark fins. They had the circularly polarized patch for the satellite, but then they had a linear polarized element at the back.
Yes, that was the
terrestrial, which did not seem a good way to do it. But anyway.
Yeah, I forgot to mention that because initially the satellite radio was incorporating two different antennas. So basically, imagine an antenna with two coaxial cables coming out and connecting to the receiver. So one antenna was linearly polarized for receiving the signals from the terrestrial towers, and then the other antenna was a circularly polarized antenna for receiving satellite radio signals. So, but then, as you can imagine, that's an expensive solution. So eventually, we were able to have only one antenna. So basically, it was just a normal, low-cost patch antenna, 25 by 25 millimeters by 4 millimeters, circularly polarized patch antenna, and the frequency is 2.34 gigahertz. So right now, satellite radio is using a simple, just one patch antenna, ceramic patch antenna.
Yeah, very interesting. Yeah, and then you did well in the trucking industry, right? And then
yes, and then after satellite radio, the as you can imagine, the trucks, in the old days, the truck only had one antenna, which is the AM/FM antenna, right? Okay. But then, as things became more sophisticated, more demanding, They started adding GPS antenna, obviously, for navigation, and satellite radio antenna for entertainment. And then, of course, data comes in. You need cell phone antennas, 5G antennas. So all of a sudden, I was designing all these antennas under one housing. So what they wanted, the customer wanted, they wanted 5G antennas, satellite radio antenna, GNSS antenna, and AM/FM antennas all in one package.
Yeah.
And that housing had to be small and low profile. So, and I think that was probably my most successful product. This multiband antenna. It solved a lot of problems for the trucking industry because now they don't need to put a cell phone antenna here, a GNSS antenna there, satellite radio antenna here, FM antenna there. I mean, it was just a mess, right? So this antenna basically have one location, one installation, and taking care of all the bands you need.
Well, I remember we came across you as a competitor, and
Yes.
you were able to get the sample and the solution out to the customer much faster than we were. And
Yes.
that's how we first met, right? So you were faster and better than we were, and we ended up doing a deal.
Yes, and I was acquired by you, and I'm really right now. I've been working now for Taoglas for the past 6 years, and I think this has been my best job ever, because when you run your own company, you have to worry about everything: invoicing, billing, shipping, management, HR. Now I only design what I like to do, what I do best. I design future antenna products.
Love it. And
Without the need for all the other boring stuff to me.
yeah, that's great to hear. And so today, like, we see the need, like you just described, about multiple antennas, more antennas that are smaller, in smaller packages, lower
Yes.
profile, etc. Have you any advice for anybody that's looking to get into the industry? Like, where can they start? What should they look at? Any tips or tricks we can give them?
Yes, a lot of university students, they really don't know much about antennas. It's really, and they don't think of, oh, I want to be an antenna engineer. There's not too many like that.
No.
But if they realize that antennas is the I would say one of the most important parts of wireless communications. So look at look at Teslas. Look at all the cars right now. In the old days, there was only one antenna on the car. It was the FM antenna, right? The AM/FM. Now there can be 20 antennas in one car for all kinds of applications, right? As we talked
Drones,
about
lawnmowers, meters, everything.
Now with AI and all this the data applications, you're going to need a lot more antennas. So you may end up needing 30 antennas for each vehicle. So there's a lot of work to be done on antennas.
Love it. Well,
And
it sounds like our future is bright. So, Argy, they're not going to put us out to pasture just yet.
oh yes,
But it's been great chatting with you. I think there's so many more topics we could talk about. But we'll put more information up on the website about the antenna efficiency and gain
Yes.
that we were talking about, so people can learn more. But that was great. So I just want to thank Dr. Argy Petros for his time. It was great to talk to Argy.
Thank you, Dermot. It was a pleasure.
Yeah, and my name's Dermot O'Shea. I'm the host of the Antenna Podcast, and you can reach out to me at dermot@theantennapodcast.com. But thanks everyone for listening today, and we'll talk to you again soon.